In this video, we're going to take a look at a fourth type of bonding that's called coordinate covalent bonding. And it's a little bit different from some of the bonding types that we've looked at before, so we need to check it as a separate category. So first off, what is a coordination complex? And here's one example. It's kind of a simple one. It's a silver with two ammonias, right? You see the NH3 right here, and then another one right here, and a positive charge. This one is a little more complicated, right? It's got a platinum, and it's got two chlorines, and it's got two ammonias. Or this one in the middle, or several in the middle, are ones that you're familiar with. So the color of blood comes from a coordination complex. Depending on whether you're human and have red blood, you have hemoglobin, or if you're something like a worm and you have green blood, you have a different compound. But you notice that all of them have metals in the middle. There's an iron. There's coppers, iron, more iron. So coordination complexes, right? Coordination complexes have transition metals plus what we call ligands. And we'll work out what ligands are and how they work in just a moment. But this type of bonding is different because transition metals have d orbitals and can do all kinds of different things with bonding. So we've got some key components of a coordination complex that we'd like to look up. And the first one is what's called the coordination number. So how many bonds the central metal ion or atom forms by the ligands. And the ligand is just the thing that forms the bond via lone pairs. So there's a couple of options. There's what's called monodentate ligands that form a single bond to the metal. These are things like single ions, chloride or iodide, small molecules, NH3, H2O, CO. They're so small that the only thing that they can do is interact once with a compound. So this cobalt here has a coordination number. This complex has a coordination number of 6. You have a cobalt, and then there's 6 slots all the way around, and a lone pair on the oxygen and water bonds to the cobalt. You notice that I've always drawn it with the O first. That's because that's what's actually forming the bond. It matters because, for example, you could have cobalts with carbon monoxide, and carbon monoxide could form up with the C bonding to the cobalt or the oxygen bonding to the cobalt, and it truly does matter. And so we pay attention and we try to write which way they form. But the coordination number is just how many total bonds to the central atom. This happens to be a coordination number of 6, right? There's 6 waters binding, 1, 2, 3, 4, 5, 6, via 6 ligands. But the number of connections can vary based on the ligand type. So this here happens to be one ligand. And it's what's called a polydentate ligand. This one's actually tetradentate because there's 1, 2, 3, 4 bonds to the iron in this complex. And so you're just counting. To get the coordination number, you're just counting the bonds. I can help you with whether it's monodentate or polydentate. By the way, dent in this case is the same root as dental, like teeth. So we kind of think of our ligands as biting onto the central metal via their lone pair. So sometimes we call them chelation compounds as well when this happens, because you've got all this biting that goes on, and chelation is from Greek for biting. Over here, our coordination number, though, there's actually 3 ligands, and I'm going to highlight them. There's 1, you notice that kind of forms a loop. There's 2, and there's a third one. This ligand is called ene, which stands for ethylene diamine. But you notice that what it does is it makes 1, 2, 3, 4, 5, 6. So the coordination number is still 6. It doesn't matter that ene is what we call a bidentate ligand, that it forms 2 bonds just by being ene. What matters is that there are 6 bonds total to the center. The coordination number is the total number of bonds. Another thing that I care about is the charge on the central metal. So for example, in hemoglobin, I can't tell from this picture, but the hemoglobin iron is a 2+. over here on the right with our cobalt-ene complex, right? We actually say cobalt-ene 3 plus. I can tell you that ene has a 0 charge, and I would tell you things like that with ligands. And so you notice that the overall complex is a 3 plus. So if ene is 0, then the cobalt has to have a 3 plus. What about our water complex? Well, small molecules like water are neutral, and so all of them are 0. And so if the whole complex is 2 plus, then the cobalt has to be 2 plus as well. So being able to assign the charge is important, because the third thing that we have to keep track of for figuring out properties of coordination complexes is valence electrons. We need to count them up. And so what I want to do is we'll ignore the iron one over here, but we'll look at these 2 cobalt complexes. And pause the video for a second, get out a periodic table, and just write down the regular neutral electron configuration of cobalt. So assuming that it's neutral and has all of its electrons. Let's see what that looks like. So I hope you found that cobalt has an electron configuration of 4s2 3d7 when it's neutral. Now, if it's cobalt 2 plus, we have to lose 2 electrons. And the rule is to lose from S first. Okay? So if I'm supposed to lose 2 electrons, they just go out here. This is the electron configuration of cobalt 2 plus, 3d7. What about over here where it's a cobalt 3 plus? Well, of course I need to lose 2, but where's the third one coming from? Well, it has to come out of 3d. And so I had 7, and now I have 6. And there is my electron configuration. Being able to count electrons is super important for what we're going to do later. So important that we're going to practice a couple more times in this video. So here are my practice compounds, and I want you to fill in all the information that you can. By the way, we have filled in a coordination number of 4 from counting our bonds on the iron, and we had filled in a coordination number of 6 over here. And we did this one on the other slide, right? We said that this was cobalt 3 plus, and we said that the electron configuration was argon 3d6. Let's fill in these other 2 on the left, because we really can't do any more on the hemoglobin. And I'll let you pause the video and try this in a second, but what I need you to understand about the way that we draw coordination complexes is that the thing in the brackets is the complex. So I purposely picked 2 versions where I've got a complex with an anion or a complex with a cation. You need to be able to separate those 2 to do this properly. So the thing in the brackets is the complex. That's what you'll use for the coordination number, for the charge, and for the valence electrons. The other thing is, of course, that the complexes don't have to be neutral, but the overall compound does. So this whole thing has to equal 0. And what do I know? Well, I know that 0 equals complex plus SO4, and I know that SO4 is a 2 minus ion. Or I know that 0 for this whole thing equals potassium, and we know potassium is a 1 plus from the periodic table, plus the complex. And so it's pretty easy to figure out that this ruthenium complex total has to be a 2 plus. That doesn't mean it's the charge on ruthenium, so watch that. And the whole complex over here has to be a -1. Again, that doesn't mean that the platinum is -1. That just means that the whole thing adds up to -1. So keep that in mind as you're working on these examples. Pause the video, try them, and I'll reveal the rutheniums. Then pause again, and I'll reveal the platinum complex. So first, I hope you saw that this is a coordination number of 6 because there's 5 ammonias and a chlorine. Second, I hope you figured out that if the whole complex has to be a 2 plus and the chlorine is a 1 minus, then ruthenium must be 3 plus to balance it out. Third, I've written the configuration of neutral ruthenium here. So let's take out our 3 electrons to finish this off. So I'll erase 2 of them from 5s. And then I'll take out 1 of them from 4d. So I'll be at 4d5. So there's my information about ruthenium. Pause and try our platinum complex. All right, just as before, this platinum has a coordination number of 6. It's bound to 1 ammonia and 5 chlorines. In order for all of the charges to balance out, this platinum has to be a +4. And by the way, platinum neutral is a little weird. It has 6s1, 4f14, 5d9. So when we make this +4, we're of course going to lose the 6s. We're not going to touch the f's, right? This is all about the d electrons. And so we just lost 1, and so we need to lose 3 more. So it'll be 5d6. So again, we've practiced counting bonds around to get the coordination number of a transition metal. We've practiced charge, so what charge is this transition metal? And we've practiced valence electrons. Super important skills for the next bit where we're going to put them to work and use them to make predictions about coordination complexes.